Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. We have reached on the lecture 6 of solid state. Yes, and my dear students, we were actually discussing about layering in crystalline solids. How in real life your solids exist, right? Yes. We also talked about the different types of layerings, the one-dimensional layering, the two-dimensional layering, the three-dimensional layering is yet to be discussed, right? Yeah. So today we'll be discussing about the three-dimensional layering. Okay. I hope till now everything is clear, because after showing you the three-dimensional layering, I'll also show you a video which will help you imagining all the layering a little bit more. Okay, so I hope all of you are excited, because I am super excited, right? Yeah, so let's start the session, my dear students. So when we talked about the two-dimensional layering, I told you that in two-dimensional layering, the layering could be your square packing or it could be your hexagonal packing, right? Yes, it could be square close packing or it could be hexagonal close packing. In square packing, I told you that it can have this kind of layers. It can have two types of basic layers, right? Yeah, in square packing, my dear students, how did we discuss this? Now let's try to understand. Ma'am, when we layer in two dimension, it could be two types. It either could be HCP, SCP, or it could be HCP, right? If I talk about SCP, then I have atoms in like this, right? Yes, and the exact same layer is below it. So this is my SCP, which is also known as AAA type of layering in two dimension. Now if I talk about HCP, then it could be something like this. This is your A layer, let's say, and in the depression of A layer, you put the other layer. So this would be, my dear students, your B layer. So what type of layering is this known as? This is known as your AB type of layering, right? Yes, perfect. These were the two types of layering which we discussed in the two-dimensional packing. Now we are moving to the three-dimensional layering. Now in three-dimensional layering, my dear students, you have a x-axis, you have a y-axis, and you have a z-axis. So now we will be discussing about these different types of layers. Okay. Now if we talk about this SCP, my dear students, now when you move into the three-dimensional layer, what you do is the two-dimensional layers which we have discussed now, this whole will become one layer. This whole will become one layer. Now this would be one layer, and the above layer would be the another layer, and the above would be the another layer. Okay, like in two-dimensional, we consider this as one layer and this as one layer. Now we'll completely discuss this as one. The above part would be the second layer and the above part would be the third layer. This is something which we will be discussing now. We'll elongate, move it into the three-dimension world, both these layers individually. Okay. Yes, I hope you're clear with this. If not, don't worry, I'll make you imagine it very easily. Okay, perfect. Now let's try to understand this. Let's say now we are going from two-dimensional. SCP, that is your close pair layering, which was AAA type of layering, to the three-dimensional part. Okay, now we are going to the three dimension. So how can it be? It can be, my dear students, in two different ways. Either you can layer, you will have the first layer same, AA type. Yes, perfect. Now what you have to imagine is that this is your A layer. Okay, this whole is your A layer. Now this whole will be considered as A layer. Now let me put the same A layer above it. Now I'll put the same A layer above it. Let's take yellow, and we'll let me take some other color so you will be able to imagine. Let's take pink color. So one layer above, exactly above it. Okay, this is again your A layer. Exactly same layer. Okay, so now I'll say that the pink part is also your A layer. So can I say, my dear students, that I am actually doing the A type of layering in three dimension? Okay, Yes. Now, how will you imagine that which particular unit cell is coming out it to be? Now, imagine, my dear students, if I try to use only these 4 parts, I am trying to use only these 4 parts. These 4 parts, okay? So, I have green atoms, so I'll put green atoms like this. I have green atoms here, I have green atoms here, okay? I have pink atoms exactly above them, so try to imagine I'm putting pink here. They are exactly above, but I just want to show you, that is the reason I'm showing you it in a different way. Now let's connect them. If I connect them, my dear students, I'll connect these two, I'll connect these two, and if I connect them like this, what am I getting? Which unit cell am I getting? I am getting the primitive unit cell. So my dear students, this is your primitive unit cell. And we have studied its packing fraction. Its packing fraction is 0.52, right? Yes. So this is how a two-dimensional square packing, on taking it to the third layer, 3-dimension AA type layering, I get a primitive unit cell. This is how you get a primitive unit cell, and the adjoining unit cells give you the adjoining unit cells in the primitive form. So if anyone asks you that in square close packing, AAAA type of layering is giving you primitive unit cell. I hope you're clear with this. Please write it down, then we'll move forward. Okay, I hope you've written it. Now, my dear students, now we understood that when we move from a two-dimensional square packing to the AA type of layering in the 3-dimension, we get a primitive unit cell, and the packing fraction of that unit cell is 0.52, right? Yes, that we have calculated, so we know that. Perfect, very good. Now, let's try to understand what will happen if we take this two-dimensional layering, AA type of layering, 3-dimension in a different way. Okay, now how a different way? Now imagine, my dear students, again the other case. Okay, so now what will happen? I have a A layer, I have to use this AA type of layering only, and in AA type of layering, one complete layer has all the same atoms together. Okay, so let's say this layering is something like this. Okay, try to imagine it. Okay, my drawing is really bad, but try to just imagine it. Okay, no, it's not coming out to be perfect, right? Yeah, but I'll try. Okay, now I can say that this is A layer. This complete would be known as A layer. Now let's take a similar layer, a layer like this. Now we are not going to put exactly above the atoms. Now where are we going to put the next layer? Just like this. See, this way, this way, this way, this way, this way. Okay, again this way, this way. So now, my dear students, I hope you can imagine that now this pink layer is also a layer, same, but it is a B layer because the position is different, right? Yes. Now you have to imagine that you put the same layer A above it again. Right? Yes. So can I say that this layering is actually known as, first I used a A layer, then I changed the position of that layer and I made a B layer, and then I used again a A layer and then again a B layer. So it is a AB type of layering in 3-dimension. It is a AB type of layering in 3-dimension. Now since it is a AB type of layering, my dear students, now let's try to imagine and draw the unit cell. First, I have to imagine. What are we going to imagine? Take these 4 atoms, okay? Just take these 4 atoms. I hope you're clear this. Now, what can we say? That you have 4 A atoms like these. Okay. Then you have, my dear students, 1 pink atom in between. Right? Yes. 1 pink atom in between. Then you have green atoms again. So you have green atoms like this again. If you join all these, what will you get? Let's join these. Let's join these. And let's join these. Can I say that it is a BCC lattice because I have 8 atoms on the corners and 1 body center atom, right? Yes. So this is a BCC, that is body centered cubic unit cell. And if I talk about the packing fraction, my dear students, the packing fraction is 0.68. The packing fraction is 0.68, right? Yes. So when two-dimensional SCP AA type of layering is further moved into the 3 dimension, if I use the AA type of layering, I get a primitive unit cell, and if I change it to a AB type of layering in a 3 dimension, I get a BCC lattice with a packing fraction of 0.68, right? Yes. This is the beauty of layering. I made you imagine how your unit cell comes out. I hope you're clear with this. Please draw them. I'll make you imagine them as well. Don't worry. Just go through it, my dear students. Perfect. I hope you have drawn it. Now let's move forward. Okay. So now, my dear students, you know that in 2 dimension we studied SCP and we studied HCP, right? Yes. SCP in 3 dimension we saw different type of layerings give you primitive and BCC lattice. Okay. And now we'll be considering the 2-dimensional HCP layering, which was your AB type, right? And now we'll move it to the 3-dimensional layering. Now when you will move it to the 3-dimensional layering, again you will have 2 different criterias. 2 different criterias. What are those criterias? Again, we will make the first layer. Now this would be a AB type of layering, right? Yes. So this would be something like this. Right? So this will be your A type of layering. Okay. Now we'll call this complete as A type of layering, and the layer above it will be called as a B type of layering, right? Yes. So now we will put exactly same layer, this kind of a layer in the what first imagine. I have to show you something. Just see this. This is a triangle, void. Can I say this is a void? This is also a void. All these white parts are your voids. Okay. Now I am taking your pink color, and if you see, then you have a triangle here as well, right? Yes. This is also a void. These are 2 different types of voids. We'll just see which type of void are these in a bit. Okay. Yes. We have white voids, right? Yes, which are the triangles which are on the upper side. And then we have pink voids. We have pink voids which are facing downwards, right? Yes. Now we'll imagine, we'll just check which type of voids are these. Now, to understand these, my dear students, to understand these, what are you going to do? You will put a B layer, you know, covering the white voids. Covering the white voids like this, like this, like this, like this, like this. Okay. Yes. So this orange one is your B layer. Okay. After layer A and B, you put a layer again. So this type of layering will be called as A, then B, then again A, then B type of layering in 3 dimension. Okay. So now, my dear students, I want you to make me understand, if you see this white void, can you say that this white void is made because it had 3 atoms like this, Yes, and a void was formed like this. Yes, and then a second layer, B layer atom covered it like this. Can you tell me which type of void is this? Which type of void is this, my dear students? If you see that three atoms are making a void and a fourth atom is above it, can I say that it is a tetrahedral void, a void formed by three different atoms? Yes. So this is your tetrahedral void. So all the white parts are your tetrahedral voids here. All your white parts are tetrahedral voids here. Okay? Yes, perfect. So this is your tetrahedral void. Now let's try to imagine which void is this pink type of void. Okay, so I had green colored atoms making a pink colored void. Something like, can I say that I had two atoms here and a one atom here. So I can say that this pink atom, this pink void is formed like this. Okay. Now, if I talk about the second layer, which was made by the orange atoms, I can see that it is formed something like, I had one atom here, I had one atom here, and one atom here. Right? So, can you just see, my dear students, that you are making a green triangle like this, and then you are making an orange triangle like this. And when is this type of void formed? Which type of void is formed like this? It is a octahedral void, because it is made up of 6 different atoms. Inverted triangles make a octahedral void, right? So I'll say that all these pink voids are your octahedral voids. Right? Yes. I hope you can imagine your tetrahedral voids and octahedral voids in this type of layering. Okay. It's clear till now. I hope you don't have any issue. Perfect. Now, my dear students, we are going to see that which type of layering is this. Now, to imagine this type of layering, my dear students, what you have to do is, we'll talk about the other part again. I am trying to make the same type again so that I'll be able to make you understand. Okay. Perfect. Now you have a orange layer which covers like this, like this, like this. It covers something like this, then like this, then like this. Now, this is something which we had drawn AB type layering. Now, what you have to do is, you'll have to erase a few things with me. Okay. Yes. Now try. Now just see, my dear students. I don't want this. I don't want this. I don't want this one part. I don't want this one part, because I want to make you understand. I don't want this and this and this. Okay. So if you see this, can I try to draw this part? Let's try to draw this part. You had 6 atoms of A layer. So I'll make 6 atoms of A layer just a little bit far away from each other. Okay. Right? Yes. And I had one atom in between. Similarly, then you had a B layer, and B layers 3 atoms are present. So I'll make 3 atoms of B layer in this position like this. And then again, I'll have a A layer, because it is a AB type of layering. So I'll have something like this. Right? And I'll have an atom here. If I try to join them, my dear students, what will I get? Just see. I'll join this, I'll join these, I'll join these, and I'll join these. Okay. So if you see it very beautifully, you can see that it is a structure of hexagonal close packing. Hexagonal close packing. This is your hexagonal close packing in 3 dimension, my dear students. And let me tell you, the Z, that is the rank of this atom, is 6. Total 6 atoms are present in it. So when a 2-dimensional HCP is taken to the three-dimensional layer, and you see the AB type of layering, it gives you the hexagonal close packing. Hexagonal close packing is your crystal unit system. Your crystal system is a hexagon, and atoms are present at the corners and 3 atoms are present in between, right? And the total rank of such type of unit cell is 6. Right? Yes. And let me tell you, my dear students, the octahedral voids are always equal to the rank. So the number of octahedral voids in a HCP is also 6. And if I talk about the tetrahedral voids, then they are always 2 times of rank. So the number of tetrahedral voids are 2 into 6, which is equal to 12. So in a HCP lattice, you have total how many? 12 tetrahedral voids and 6 octahedral voids. This is the beauty of chemistry. I hope you can imagine this. Please go through it. It is very, very important. I'll have some water, draw these, and then we'll move forward. Okay? Perfect. I hope you're clear with this, because this is the most important part, my dear students, to imagine. Take your time. Try to imagine it. Okay? Yes. So this is something which I wanted you all to imagine, so that you will be very clear with the concept. Okay? Perfect. Now let's move forward, my dear students. Now let's move forward. Now we are going to discuss about the, I hope you've written it. Now we are going to discuss about the two-dimensional HCP, and now which was your AB type of layering. Now I will take it to the three-dimensional in a different way. Okay, what was the different way? One way we had studied in 3-dimension AB type layering. Now, my dear students, what are we going to do? Just imagine you have one layer here, one layer here, one layer here, one layer here. Then you had a layer here, right? So this is complete A layer. Then you had a B layer. Let's say B layer is covering this. So it is covering these voids. Right? Can I say that this is a B layer? Now, I have a third layer as well in this type of layering, and that actually covers your these atoms. Which atoms? Your, just a second. Huh? Yeah. It covers your these layers. Okay. So this is your, it covers your octahedral voids. This is your C layer. So the layering here is your A, B, C type. Okay. And this type of layering gives rise to, my dear students, your CCP structure. The packing fraction is 0.74. You can say CCP or you can say FCC. You need not imagine this, because this is too complicated for your syllabus, my dear students. You just have to remember that in 3-dimension, when we do HCP lattice into the 3-dimension and we do ABC type, it gives us CCP or FCC lattice, and the packing fraction is 0.474, and that is the most that you want to understand in this particular part. Okay, yes. One important thing which we haven't written here, the packing fraction of HCP is also 0.74. Okay, the packing fraction is also 0.74. Please write it down. Perfect. So this is what you can talk about the third type of layering. Okay, I hope you're clear with this. Please write it down. Okay. Okay, perfect. Now let's try to draw the FCC lattice. Can we draw it or not? That this part which I am going to discuss now is out of your syllabus. I just want you to imagine it, so I am making it for you. Okay, so first layer is A. So let me say that A layers, you have one atom present. Okay, then you have a B layer of orange color. So let's draw a B layer. So this is your B layer. Then you have a C layer of green color. So this is again your C layer. Okay. And then you have again A layer. So, okay, it was of pink color. I'll have to draw it with pink color, huh? Because C layer was with pink color. This was your C layer. And then you had again a A layer. So your A layer is here. So now, how are you going to imagine it? It is very, very beautifully understood. You join these like this. You join these like this. You join this with this. You join this with this. You join this with this. And you join this with, just a second. Okay. I hope you can see that how a face-centered cubic unit cell comes out to be. There are atoms on the corners and there is one atom on each face center. This gives you your FCC/CCP lattice. Okay, you need not imagine how it came out to be, but when you rearrange these atoms, you get a FCC lattice like this. Okay, this is out of your syllabus. This was only for your imagination. I hope you're clear with this. These are the few things which you need to remember, my dear students. I'll make you revise everything, and also I'll show you the very beautifully the videos as well, so that you will be very clear. Now first let's try to imagine it. Okay, now first let's try to imagine it. You've written it? Please draw it. Pause the video, draw it, and then we'll move forward. Okay, I hope you've drawn it. Now let's try to revise. So the topic would be revision. So now when we revise, my dear students, what will I say? That we started from the two-dimensional lattice. Okay, when we started the layering of two dimensions, so I'll say two-dimensional layering. In two-dimensional layering, I had two possibilities. And those two possibilities were either it could be a square packing or it could be a HCP packing. If it was a square packing, it would be AA type, and if it was a HCP type, it could be ABAB type. Right? Perfect. I hope you don't have any issue till now. Right? Yes. Then from here, we moved forward to the three-dimensional layering. Now from here, it could be your three-dimensional layering. And this could have two possibilities. The one possibility was if you incorporate AA type of layering again as your AA type of layering only. Right? Yes. If it was AA type of layering, I would get a primitive unit cell. And if I get a primitive unit cell, the packing fraction of this unit cell would be 0.52. Right? Yes. And if I didn't go with AA type, I went with ABAB type layering. And if I went with ABAB type layering, I would get a BCC lattice. I would get a BCC, that is body centered crystal system, and the packing fraction would be 0.68. Right? Yes. Now let's try to take this to the three-dimensional layering. If this went to the three-dimensional layering, my dear students, what will happen? It can have two possibilities again. Either it could be ABAB type of layering, right? Yes, ma'am. Either it could be ABAB type of layering. Then it would be HCP, my hexagonal close packing in the three-dimensional layering, and the packing fraction would be 0.74. Right? Yes, and the rank would be equal to 6. I told you. Perfect. And if we talk about here, it could be ABC type of layering. And this would give me CCP or FCC lattice, and again the packing fraction would be 0.74. Right? Yes. This is the complete flow chart that we have studied in the layering part. And this is very, very important, let me tell you. I hope you're clear with this. Perfect, my dear students. First write this flow chart and then I'll show you the video. I hope you've drawn it. Now let's try to imagine each and everything using this video. Okay, the three-dimensional modes which we are going to study. I hope you can see the complete video here. So in one-dimensional close packing, there is just one way of arranging the species. I told you only one way of arranging the species, and it could be, I'll just fast forward it a little bit. I'll increase the speed to, let's say, 1.5. Okay. So if you imagine here, my dear students, this is the one dimensional layering, and this is a atom in between. You have to see its coordination number. It is directly connected to two atoms, so the coordination number is 2. I hope you're clear till now. Yes. Okay, just one way of arranging the spheres. The coordination number is 2. This is what it is showing you. Next, my dear students. Next is close packing structures in 2 dimension can be generated by stacking rows in one-dimensionally close packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Now they're talking about the 2-dimensional layering. Okay, so now let's see the square packing. You will have a layer. Okay, and then you'll have exactly same layer above it, AA type layering. Okay, again a AA type layering. This is what is known as in two dimension AA type of layering. If you see one atom, it is directly connected with 4 different atoms, right? So the coordination number here would be 4, right? Yes, so the coordination number here would be 4. And this is AAA type of layering. That is the reason we call it as AA type of layering. AAA type of arrangement in square packing, right? Yes, perfect. Now let's talk about hexagonal. What will happen in 2-dimensional hexagonal? The second layer will come and sit in the depressions. Yes, it is sitting in the depression. So this is A layer, then B, then A, then B, then A, then B. Okay, so this is what is happening here. This is A, this is B. And now since the other layer would come exactly like A, it would be again a A layer. And now just see, my dear students, you have 1, 2, 3, 4, 5, 6. How many 6 atoms are directly connected? So the coordination number is 6. Okay, perfect. Beautiful. Right? Yes. So this is AB type of arrangement of hexagonal close packing. If we compare the square packing, we get this visual, and if we see the hexagonal close packing, we see this. So we see that here empty space is more and here the empty space is comparatively less. Okay. Beautiful, beautiful. These are known as your void. You have a square planar void here, and you have which void there, my dear students? Triangular void. Okay, so the packing efficiency of that particular part would be more because void space is less and here void space is more. Now let's try and discuss about the 3-dimensional layering. Now in 3-dimensional layering, we'll move from the 2-dimensional close packing to the 3-dimension. So now this whole complete layer will be known as A layer. Okay, this whole layer will be A, and now the other layer will be exactly like this. That is the reason that is also A layer. So A layer above A layer. A layer above A layer. So this is AAA type layering in 3-dimension. And now we'll see which unit cell comes out. It comes out to be the okay, it's showing you that the coordination number is 6 because each atom is connected by 6 different atoms. Okay, yes, perfect. Now we'll see which unit cell comes out. Okay, AA type of layering in 3-dimension, and the unit cell, if you see, is the primitive unit cell. Simple cubic unit cell or the primitive unit cell. Okay, yes. Now let's talk about the hexagonal close packing. That is your now this complete layer will be known as A, and the layer exactly coming above is the B layer. So AB type of layering, placing second layer over the first layer. Okay. You have triangular voids here. Now this is your complete one layer, and you Repeat it as AB type of layering. Again, you can see the coordination number. These are the voids. The blue parts are your voids. Those are two types of voids, tetrahedral void and octahedral void. Right? Yes, perfect. This is a triangular void, and if you put one atom over this, this is your tetrahedral void. This is your tetrahedral void. The empty space, okay? Covered by 4 atoms or made by 4 atoms basically. This is the octahedral void. The opposite triangles. The opposite triangles, my dear students, is a octahedral void. Right? Perfect. Beautiful. Beautiful. See the opposite triangles. I hope you can imagine the opposite triangles here. So this is the definition. In case we need to calculate the number of tetrahedral and octahedral voids in a crystal system, then just knowing the number of spheres will serve the purpose, right? Yeah. Suppose there are n spheres in the crystal system. No, we don't need this discussion. We just want to see the voids and layering. So now let's talk about the layering here. Let us place third layer over the second layer now. Okay. One layer will be covering only tetrahedral voids and the other would be covering the octahedral voids, and this will give you your FCC lattice. These are your tetrahedral voids, and if you cover your tetrahedral voids, this is the type of layering happens. Right? Yes. Beautiful. Beautiful. It has made you imagine everything so beautifully, right? Yes. This is your A layer, then B layer, then again A layer. In 3-dimensional HCP, if you have a AB type of layering, you get a hexagonal close packing HCP. Coordination number 6. Hexagonal close packed structure, AB type pattern. See, beautiful. This is the type of structure that comes out to be. You have 6, you have 3 atoms, you have 3 atoms. Either you draw it like this or you'll have exactly like this above and you will get a hexagon. Right? Coordination number would be 12. Perfect. And if you cover the octahedral voids as well, you will get a FCC lattice or CCP lattice. Right? Yes. Beautiful. It's almost done. Just a second. It's almost done, my dear students. Now this is A layer, B layer, and the C layer is covering your octahedral voids. It is covering your octahedral voids. This is the ABC pattern. Okay, beautiful, beautiful. And it gives you a CCP or the face-centered cubic unit cell. And the coordination number is again 12. Okay, perfect. Okay, my dear students, I think we are done. Now we can move forward. Everything is revised till now, whichever thing we have discussed. So please pause the video, try to understand each and everything, and then we'll move forward. Okay, I hope you've written it. Now let's try to solve the questions. Let's try to solve the questions. The first question is on your screen and you have to try to solve this question. What does the question say? The question says that which of the following layering pattern will have a void fraction of 0.26? Now, my dear students, if it says that your void fraction is 0.26, if the void fraction is 0.26, can I say that the packing fraction would be 1 minus the void fraction? So this would be 1 minus 0.26. So this is equal to 0.68. Right? Yes. And if the packing why is 68? What calculation have I done? 1 minus 0.26, na? Yeah, it is 0.74. Yes, it is a 0.74 packing fraction. Now, if your packing fraction is 0.74, this means that either it is HCP or it is FCC. C, right? These both have the packing fraction of 0.74. Right? Yes. Now, my dear students, if SCP and FCC has the packing fraction of 0.74, then it is a close packing. Either it is a AB-AB type of layering, because HCP is AB-AB type layering, or it is a ABC-ABC type of layering, because FCC is a ABC-ABC type of layering. So now let's see. It is ABC, then it is CBA. No, this is not the correct answer. ABB, this is not correct answer. ABC, ABC, ABC. Yes, option C is correct, and this is again wrong, because there is no AB-AB type layering. There is only ABC type of layering, one given. So option C will be your correct answer. I hope you're clear with this. Perfect, my dear students. You can pause the video and write the answer. Next question. Next question says that the coordination number of a metal crystallizing in a hexagonal close packed structure is. So my dear students, hexagonal close packed structure, it refers to the three-dimensional either HCP or FCC lattice, and both of them had the coordination number 12 each, right? Yes. So the direct answer here is 12. So option A is the correct answer. We saw in the video the coordination number in the three-dimensional layering of AB, though that HCP lattice or FCC lattice, the coordination number will always come out to be 12, and the packing fraction will always come out to be 0.74. So option A will be your correct answer. I hope you are clear with this. This was the most easiest question and the direct question that could be asked, right? Yes, perfect. Please write it down and then we'll move forward. Let's talk about the next question. Next question says that the atomic radius of strontium is 215 picometer. So it is giving you the radius of an atom which is 215 picometers. And it crystallizes with a cubic closest packing. So it crystallizes with the cubic closest packing. This means that it is talking about the CCP lattice, or we could say FCC lattice. So it crystallizes in a FCC lattice. Okay, edge length of the cube is, so you have to tell the edge length of the cube. So my dear students, in FCC, can I find the relation between R and A? Yes, if I found the relation between R and A, I can find the edge length. I know that for a FCC lattice, I have the crystal system like this, and my atoms are present on the corner, as well as they are present on the face centers as well, right? Yes. And I also know that atoms do touch each other along the face diagonal. So this would be my one atom, my second atom, and my third atom. And let's say we are talking about this is A and B, so this is your A and B, right? Yes, we did talk about this, my dear students, that since it is a A edge, it is also edge length A, and this will be equal to total 4R, right? Yes. So can I say that 4R, this is 4R, this is 2R, R and 4R. Yes. So can I say that AB square is actually equal to 2, this would be A square plus A square, so 2A square. Yes, ma'am. So AB will be equal to root 2A. And what is AB? 4R. So 4R is equal to root 2A, my dear students. So A would be equal to 2 root 2R. Yes or no? Yes. So 2 root 2R, and what is the radius given? 215. So the edge length would be equal to 2 into 1.44 into what is the radius? 215. So just multiply it and you will get your answer. So just multiply it and you will get your answer, right? Yes. So this is how you had to solve this question. The most tricky part was it crystallizes with a cubic closest packing. You need to understand that if it is talking about cubic closest packing, this means that it is talking about the CCP lattice, okay, or the FCC lattice. I hope you got the answer. Please pause the video, write it down, and then we'll move forward. Next question. Next question says that in a hexagonal close packed structure, that is you have a HCP structure, in a hexagonal close packed structure of spheres, the fraction of volume occupied by the sphere is A. Let's say you have SCP and the atoms present here are A, and the fraction of volume occupied. This means that the packing fraction is given to be, let's say, A. Okay, perfect. In a cubic close packed structure, next you have a CCP/FCC structure. In a cubic close packed structure, the fraction is B. Let's say your atoms were B and the packing fraction is B. Yes. What is the relation between A and B? My dear students, the packing fraction for HCP is 0.74. The packing fraction for HCP is 0.74. The packing fraction of FCC is 0.74. It is exactly same. Yes, their structures are different, but their packing fraction is exactly same. So I'll say that A is actually equal to B. So A is equal to B. So option A will be your correct answer. So this is how you will be solving this type of question. Perfect? Yes, perfect, my dear students. Let's move forward to the next question. The next question is on your screen. Try to solve this question. The question says that the unit cell present in ABC closest packing of atoms is. A very easy question, a very easy question. If I see ABC layering, this means that I am talking about the three-dimensional layering, which I came from two-dimensional HCP lattice, and I got either two types of layering. Either I could get AB type, and this would give me rise to HCP, hexagonal closest packing, and I could get ABC layering, and this could give me FCC or CCP lattice, right? Yes. So since it is talking about ABC type, so it is talking about this type. So ABC is face centered. So option C will be your correct answer. So this is how you'll have to solve this question. So easy question, right? Yes, perfect. Please write it down and then we'll move forward. Let's move to the next question. The next question says that the unit cell present in AB closest packing of the atoms is exactly same, my dear students. You went from two-dimensional HCP lattice, which was your AB type, to three-dimension. Now it could be two types. Either it could be AB type. This would give you your hexagonal closest packing, or it could be ABC type, and this would give you FCC/CCP lattice, right? Yes, it is talking about AB, so it would be hexagonal. So option A will be your correct answer, right? Yes, perfect. Please write it down. I hope you've written it. Now let's move forward to the next question. The next question says that which one of the following schemes of ordering close packed sheets of equal sized spheres do not generate a closest packing layer? If in any case my layer, one layer is exactly same to the bottom layer, it is never a closest packing. This means that if you have a layer like this and you have exactly same layer like this, then this is not a closest packing. This is not close packing. When is it considered a close packing? It is only considered a close packing when you have atoms like these and you have atoms in the depression of the first layer. Only then it is known as your close packing. Okay, so I can say that ABC, yes, it is a close packing, because no layer is getting repeated here. If I talk about here ABAC. So my dear students, which of the following schemes of ordering close packed sheets of equal sized spheres do not generate a close packing? They do not generate. Okay, so I'll say that this does generate close packing. A, then B, then A, then C, then A, then B, then A, then C. Nothing is repeating, so this will also generate a close packing. If you see here, after A you are getting B layer and then again you are getting B layer. This will never give you a close packing because one layer is repeated with the other layer. Here you have A, B, C, then you have B, then C, then A. Nothing is repeating, so this will also give you close packing. Only one will not give you close packing, that is option C. So option C will be your correct answer. Okay, Perfect. I hope you're clear with this. You can write it down. It is something very important. I'll just draw it more beautifully. You have one layer and you have the same layer repeating it. Okay. So this will never give you close packing. This will give you close packing. In the closest packing of atoms, there are, my dear students, you know that in close packing there are tetrahedral and octahedral voids, but in the not close, the packing which are not close, they do not have tetrahedral and octahedral voids, right? And also you have tetrahedral voids equal to 2 times of rank, and you have octahedral voids exactly equal to the rank, right? Yes. So can I say that your octahedral voids, 2 times of octahedral voids are your tetrahedral voids, right? Yes, for every octahedral void, you will have 2 tetrahedral voids. Okay, so for every 2 tetrahedral voids and 1 octahedral void per atom, so option B will be your correct answer. So option B will be your correct answer. I hope you are clear with this, right? Perfect, my dear students. Please write it down and then we'll move forward. Next question. The question says that the coordination number of a metal crystallizing in a hexagonal close packed structure is, since it is getting crystallized in a hexagonal close packed structure, the coordination number would be 12, right? Yes. So option A will be your correct answer. Direct question, my dear students. Direct question. I hope you're clear with this. Can we move forward to the next question? Let's move forward to the next question. The next question says that in a solid, oxide ions are arranged in CCP. So you have oxide ions and they are arranged in CCP lattice. Then you have cations A and occupy 1/8 of the tetrahedral void. So they cover 1/8 of the tetrahedral voids. And then you have cation B, which covers 1/4 of the octahedral voids. You have to tell the formula of the compound. If it crystallizes in a CCP lattice, can I say that the rank is actually equal to 4? That I know. Perfect. CCP means FCC. Rank is 4. How many tetrahedral voids? 2 times of rank. So it is 2 into 4, which is equal to 8. And how many octahedral voids? Equal to the rank, which is equal to 4, right? Yes. So if you have oxide ions present, so this would be 4. This would be 1/8 of tetrahedral voids, which is 8. 1/4 of octahedral voids, which is 4. So this would be 4, 1 and 1. So the ratio is 4:1:1. So the formula would be AbO4. So AbO4. Is there any option as AbO4? There should be an option of AbO4. So definitely here a 4 is missing. So option A will be your correct answer. Okay. I hope you are clear with this, my dear students. Right? Yes. Perfect. Please write it down and then we'll move forward. I hope you've written it. Now let's move forward. Next question. In a face-centered cubic arrangement of A and B, so you have a face-centered cubic arrangement. So the rank is equal to 4. So, and you had A and B. I'll write it here. A and B. In a face-centered cubic arrangement of A and B atoms, whose A atoms are at the corner of the unit cell. So the A atoms are present at the corner of the unit cell. Unit cell has 8 corners. So all the 8 corners are covered by A, right? Yes. And the contribution at each corner is 1/8. So can I say that 1/8 of 8 is the actual A atoms present? Till now, what I know, right? And B atoms are present at the face centers, and B are present at the face center. The contribution at face is 1/2, and the total number of faces are 6. So 1/2 into 6 atoms of B have been used. Now, one of the B atoms missing from one of the face in unit cell. Now what happened is, it would be the case, but one of the B atom was missing. So I had one complete atom of A and I had 3 atoms of B. 3 atoms of B. But out of this, one is missing. right? So I have one atom of A and I have two atoms of B, right? The formula of the compound would be AB2, right? In a face-centered cubic arrangement of, okay, no, only one atom is missing, not complete one atom. It is saying that from one face an atom is missing. The line should be B atoms, one of the B atoms from one face. Okay, it is written here, missing from one face of the atom. Okay, now let's try to understand this. See, my dear students, it says that initially you had 8 atoms on the corners. The contribution was 1/8. Okay, and you had 6 faces and the contribution is 1/2. But what actually happened is that one of the B atoms was missing from any one of the face. Only one of the face atom was missing. So there were not 6 atoms present on 6 faces. Only 5 atoms were present and one atom from one face was missing. So here out not 6 and 5 will come. Right? Yes. So this would give me 1 and this would give me 5/2. So the formula would be AB 5/2. Is any formula like this present? No, it is not present. So what will you do? You will have to simplify it a little bit more. Try to multiply. Take the LCM, multiply by 2. So this would be 2. This would be 5/2 into 2. So 2 cancels. So this would be 2 and 5. So the formula would be A to B 5. So A to B 5 is your correct answer. So yeah, A to B 5, that is option C will be your correct answer, and you have to solve such types of questions seeing the options. Okay, whether you have to simplify it or not, just check the options and accordingly calculate your answer. I hope you're clear with this. Perfect, my dear students. This was all about layering, my dear students. This was all about layering. I wanted to cover the defects today as well, at least start the topic, but then I thought that no, I want all of you to have a clear picture of layering today. Try to read this part from the NCERT, try to draw the diagrams yourself. Okay, only then you will have a better picture. You can replay my video again and again, but you should have a very clear understanding of the layering, my dear students. It is the heart of solid state. This is the part from where solid state actually began. Okay, yes, in the next lecture we'll complete all the defects. Don't worry, we'll complete all the defects in one complete lecture. Do come revise, read the NCERT about the solid defects. It is completely theoretical part, nothing very formula based questions are asked. It is theoretical part, so we'll cover that in the next lecture. Till then, keep studying. All the very best. Thank you so much.